Thanks so much, Rob. Wow, it's a thrill to be up here in front of all of you. I was just thinking back to getting my PhD in the end of 2005, and then I moved to England, and I met Rob in 2006, and oh my gosh, it's been 20 years. Look at me. That picture that you just showed is from 10 years ago. I'm a lot grayer now. I'm thrilled to talk to you about Gaussian processes. That's what I did my PhD dissertation on. I'm hoping the French slides will come up soon, but I'll just keep talking while we're waiting. Yeah, I moved to England, and I thought I was going to study something different. But then I got an invitation from Hugh Chipman, who you guys probably know, to come give my very first talk in an invited session ever. I was a postdoc at the time, and I was totally thrilled. And it was at the Statistical Society of Canada meeting in London, Ontario, so not too far from here. And I told him, I don't have any money, I can't come. And he was like, don't worry, I'll pay for it. And you can come visit me in Acadia. And I did that, and I just had such a blast. I taught him what I knew about Gaussian processes, which is what kind of laid the foundation for a book that I wrote that I'll show you a little later, and this talk. Should I just keep going? You think so? Okay. All right. Gaussian processes are popular in a number of application areas. I work on computer simulation experiments, and so a lot of my examples will be biased towards that, but people use them in spatial statistics for geospatial modeling, and it gets used in machine learning as a general purpose prediction machine. Computer experiments, my area, so you use a computer experiment wherever you can't study the physical system directly because it's too expensive, too difficult, unethical. Fantastic examples. A lot of mine come from aeronautics, but they also get used in epidemiology. You can't just make people sick and watch what happens, right? But you can do that virtually. So a computer experiment is a virtual experiment of a physical system usually, but maybe also a social system through mathematical modeling and the computer implementation and solving of those mathematical models. I'm going to circle back at the end of the talk here to a cool aeronautics example that involves computational fluid dynamics and a computer code that has 7 inputs, and then the output that we're modeling is the lift over drag ratio. And each run of this computer experiment for one of those 7 tuple of inputs takes about an hour on a supercomputer to solve the system and then give you out the output. So under the hood, it's a regression problem. I've got to plan an experiment in this 7-dimensional space and then run my code at that batch of runs and get the outputs and then try and do something with it. We're going to solve a quality problem. I'll tell you about an optimization problem that you might do with computer experiments sort of in the middle of my talk. We talk about surrogate modeling, but that's really just regression. We're going to fit a nonlinear regression and use that fit to do something with our data. Any good surrogate or regression should furnish accurate predictions of the real system or the system being studied with good uncertainty quantification. And the quickly part, the third bullet there, is really important in my area, because if you can't do it quicker than an hour, say, then you would have just run the computer code instead. So you got to be able to do it pretty quickly in order for it to be useful. Okay, so here's the outline of the talk. I think it's super important to give you a tutorial in a talk like this. So the first part of this is going to be a tutorial on Gaussian processes. And my favorite application of Gaussian processes to Bayesian optimization. That's going to be a big chunk of it. I've got a survey of the frontier of the state of the art in the middle, and we might go a little bit more quickly through that so we can get back to that aeronautics example. I want to tell you about deep Gaussian processes, which are an area that I've been working on very recently, and I want to talk to you about that airfoil experiment. Okay, so what is a Gaussian process and how do we use it for surrogate modeling? I think it's helpful to start with how you might generate a random function using a multivariate normal distribution, because at its heart, that's what a Gaussian process is. So if you specify some inputs x, n of them, I'm just thinking in one input dimension for the moment, but it can be in any input space. And then you build a covariance matrix with those inputs using inverse distance. So I've got an n by n covariance matrix, and the ij entry of that is the distance between xi and xj in the reciprocal. So e to the minus that Euclidean distance. So I'm going to build an n by n covariance matrix with those inverse distances, and then use that to draw a random n vector y. And that random n vector represents a finite distribution or sample from a finite distribution over functions, and then I can plot that in the xy plane. And there's R code up on the slide. There's R code throughout the talk. This is a reproducible talk for the most part. I'll show you some box plots later summarizing results that were not run in real time. We're not going to go through the code. It's really just there to give you the feeling that this isn't that hard because it's not that many lines of code, and that what you see is what you get, which I think is a really important feature for this presentation. Okay, so here is 3 example functions that were generated in this way. So each one of those lines is one random n vector y plotted as a function of the inputs x, which are just a grid from 0 to 10. Okay, so random functions from a multivariate normal distribution where the covariance structure is a function of distance. And the mean is 0. The mean can be something else if you wanted to, but for this whole talk, the mean is going to be 0, because a lot of the action of Gaussian process of regression is in the covariance structure. Okay. Now, for regression, we really want to solve the inverse problem. If someone gives us some examples of a function, some xy pairs as training data, we want to know what random functions under a Gaussian process prior, like I just showed you, could explain those data points. And the way that you do that is by borrowing an important result about multivariate normals. You used to find this in the appendix of a good graduate text in statistics, but now we just get stuff off of Wikipedia. Or maybe that's even old-fashioned. Maybe we just ask Claude. But be careful. Don't ask Claude for too many things. Use your head. Okay, so here is a copy from the Wikipedia page on multivariate normals. It says if you have a random vector y that you partition into y1 and y2, and you also partition its mean vector and its covariance matrix into components corresponding to y1 and y2, then you can derive the conditional distribution of y1 given y2, or vice versa. But the way that I have it written on the slide is for y1 given y2. That's also Gaussian, because many operations for multivariate normals are closed. That is, they're also multivariate normal or univariate normal. So you get some equations for the mean, which are a linear projection in this n-dimensional space, and a covariance which has a quadratic form that reflects learning. Your covariance will go down when you condition on data. So I can use that with training and testing data in a regression context. So if x and y represent my training data and squiggly x represents where I want to predict my testing data, I can derive the conditional distribution of the testing on the training by following this Wikipedia conditioning result for multivariate normal, and get some equations, a mean vector and a covariance matrix, describing the Gaussian predictive equations at new inputs squiggly x. And that's what they look like. These are called the Kriging equations. I think they were first written about by a South African statistician in the 50s, and then popularized in other geostatistical contexts after that. They have many nice properties, but I'm not going to go into them. I'd rather show you this in action. So suppose I have some training data. The code here just implements 8 observations of sine of x for x's in one period of a sinusoid. It's a very simple computer experiment where the computer simulation is really just sine of x. So I calculate distances between all of the pairs of these 8 points, and then I create a testing grid, and I calculate the distances between those locations. And then the most important thing is the distances between the training data and the testing data, because that's what's involved in the projection in those Kriging equations. So here's just some code that does that. Then the top 3 lines of the file here are that linear projection. So I need to invert the covariance matrix, then I need to solve a linear system and form the covariance as a reduced quadratic form. And then I can show you the result in any number of ways, and the code supports showing you draws from the predictive distribution, but also mean and error bar summaries of that distribution, and that's on the the next slide. So again, going back over it, each of those dots is an evaluation of sine of x. The x's are equally spaced from 0 to 7 or so, 2 pi. And I've calculated these distances, and I've developed this conditional distribution using those distances. And the black line is the mean of my prediction, the mean of that Gaussian distribution. The red dashed bars are error bars. Those are 95% quantiles from the diagonal of the covariance matrix that I calculated. And each one of those gray lines is one of 100 random draws from that predictive distribution. Sometimes people talk about the sausage shape of a Gaussian process predictive surface because it kind of looks like a sausage, right? I'm interpolating this function. This is really important in many computer experiments applications because many computer simulations are deterministic. So we're often interested in interpolating. But there are others where the simulation is stochastic. And I've got some examples of stochastic simulations coming a little bit later. All right, I showed you a very simplistic multivariate normal covariance structure involving inverse distance. Many, but not all, involve inverse distance. Here is a slightly fancier covariance structure that still involves distance, but introduces some extra parameters controlling the scale of the covariance. That's the new parameter. A noise parameter, tau squared, allowing me to fit noisy data. And I've got what are called length scales, theta. Those are kind of like the regression coefficients, beta. You've got one for each input direction. But this isn't linear modeling. It's nonlinear. This theta parameter is in the denominator of this squared distance. So it's controlling the rate of decay of correlation as a function of distance in each input coordinate. So these are just parameters, or sometimes we call them hyperparameters, but it's not really worth going into why. And just like anything in statistics, you can dial in settings of those hyperparameters with your favorite method. If you want to use estimating equations, you can do that. If you want to use method of moments, you can do that. If you want to use the likelihood via maximum likelihood, which I'm going to show you in a moment, you can do that. If you want to do Bayesian inference and sample from the posterior distribution, you can do that. What I've got up on the slide is that some of the parameters have a degree of analytic tractability, which means that you can, for example, take the derivative of the log likelihood, set it equal to 0, and solve in closed form. For example, the scale parameters that way. If you were doing Bayesian inference, you could give it a reference prior and integrate it out in closed form. For other parameters, you don't have as much analytic tractability. You can still take derivatives of the log likelihood, which you can use for maximization numerically, or you can use in your favorite Hamiltonian Monte Carlo setup. But it's a little bit more work. It's not a lot. And one of the things I learned as a postdoc in Cambridge after I went there is you can solve a lot of problems if you can take derivatives in statistics, right? So many things involve taking derivatives. You can take derivatives of your log likelihood in particular. You're pretty golden as far as inference goes. So I've got some code here that is too many lines of code. Don't look at it. But it's only 20, right? It's not like I just showed you a whole 10,000 line computer code. Implementing the log likelihood with that new covariance structure and its gradient. And I can put that log likelihood and gradient into my favorite optimizer and dial in parameters for it. So let me show you another example where I'm doing that. Here's a two-dimensional example. So I mean that the inputs x are in 2D, and then the response is a nonlinear function of those two inputs. And I'm just taking some training data, 40 xy pairs that I generated from this response surface, and I put in the negative log likelihood into it and its gradient into the optim function in R and asked it to optimize that likelihood surface and give me some parameters. The values of the parameters themselves are not super interesting, and maybe this is why they're called hyperparameters, because you just take those values and you put them into the covariance structure and rebuild your covariance matrices with those and develop your predictive equations. And really a lot of the action is in that multivariate normal conditioning, not in the specific values of the parameters themselves. Okay, so once I've got those parameters and I put them into my Kriging equations, I can then make a grid of testing locations in this two-dimensional input space and then show you the mean over that grid and the variance over that grid. So here that is. The training data, the x-coordinates of the training data are shown as open circles on the right-hand panel plot. I'm not showing you the outputs, the y values, but I am showing you the mean predictive surface. That's the mesh on the left, and then the predictive standard deviation on the right. And you can see that standard deviation is lower, that's red, nearby the training data input coordinates. And it's higher in yellow away from those. So this is the sausage just in a two-dimensional space. You can do this in any input dimension. Obviously, in higher input dimension, you need more training examples in order to learn, at least in order to learn efficiently. It's hard to learn a function of 7 input variables. But from an operational perspective, from how you would code it up, it's really no different than what I just showed you. So here's an example in, let's see, this is in 5 input dimensions, I think, the Friedman function. Jerry Friedman wrote this function down in his paper on multivariate adaptive regression splines. It's another nonlinear prediction machine, a competitor to Gaussian processes. It has, it's got interactions in it, it's got quadratic relationships, it's got a sinusoid, and it's got some linear components. Anyway, I want to fit that, right? So I can just take those xy pairs and put it into my optim function with the same negative log likelihood and gradient, and I'll dial in length scale parameters and other hyperparameters of that covariance structure, and I can use, the code is all the same as before. Or if you want, there's tons of libraries out there that will automate all of this for you. I'm going to use a library called LAGP that I wrote because I am familiar with it, and I want to use it downstream for some other stuff later in the talk, but there's lots of great ones out there in Python, in R, in MATLAB, whatever you use, in Julia, and so on. And the punchline of this slide is at the very bottom. When it's really hard to visualize a 7-dimensional function. There are ways I could do it, but I'm just going to show you that when I make a prediction and compare it to something else out of sample, I get a more accurate predictor than many other methods. One of them in particular is the Mars method that Jerry dreamt up to illustrate this, or to work with this data. So I get a lower root mean square prediction error. That's the number at the bottom, the 0.54. Okay. Of course, that's just one very simple example. You should go try these things on your own and see how they work. Now I want to tell you about my favorite application of Gaussian processes, which is to the sequential design of experiments, or what in machine learning they call active learning. The idea is that you use your model fit to suggest future training data in order for your fit to learn about the input-output relationship efficiently. So you want to create a virtuous cycle between data acquisition and model fitting, or learning. Okay, so there's a little diagram that says, maybe start with a small capital N, fit a model. I'm thinking Gaussian process model, but you can do this with all sorts of different models. Use some aspect of that fit. I'm going to use the predictive equations, the predictive mean and the predictive variance and covariance. But you can use other things to make a decision about a new input coordinate to try. Then you get the output at that input coordinate, which for a computer simulation experiment is pretty easy. You're just putting those x's into the computer program and waiting for it to give you the y's. And then you augment your data and repeat. What criteria you use to choose the next point, the so-called acquisition criteria, depends on your goal for learning. I'm going to show you 2 in this talk. The very first one is for what's called Bayesian optimization. Here, I don't necessarily care about the whole response surface for my xy pairs. I care about the x-coordinate where the output y is small, is the global minimum. So I want to solve this mathematical program. I've got some function f that's running a computer simulation and giving me an output, and I want to know the coordinates x that minimize f of x. And I'm going to find that through experimentation, through active learning, choosing an acquisition criteria that focuses my learning effort near promising locations to minimize the function. A tacit constraint here is that I want to evaluate the function as few times as possible, right? It's expensive to me. I've got to run a computer simulation on a supercomputer, and I've got to wait an hour. So I want to minimize my use of that resource. I want to find the minimum quickly or efficiently by running the code as little as possible. There are many acquisition criteria that people use for Bayesian optimization. This is the most common and my favorite. And it's also Canadian. Jones, Schoenlau, and Wells. So Matthias Schoenlau, is there any chance he's in the audience? He works nearby. No. This was his PhD dissertation at Waterloo. I think he's at Western Ontario now. Spectacular work. I asked him one time if he ever predicted that this would be as big as it is. It's absolutely huge. Maybe not so much the way that I'm presenting it, but in other machine learning areas, Bayesian optimization is the go-to. And his idea, which is called expected improvement, is the default way to use Gaussian processes for Bayesian optimization. So what you do is you define a random variable called improvement. Improvement is the random amount by which a testing location x, its output y, is below the current best minimum that I'm calling Fn min. So if Fn min is the current best low value that you have in your training data set, your Gaussian predictive equations predict some amount by which that output y is below that current best minimum. You take the expectation of that under that Gaussian predictive distribution, which can be done in closed form. It's a great example of integration by parts and by substitution simultaneously. So it's complicated, but it's not rocket science. And you get this nice equation that is, I think of this as a lens through which you look at the predictive distribution. The predictive distribution is this multivariate normal, but what you really care about is its potential to improve on the minimum. And let's see if I can get the pointer right here. So some of that has to do with the mean, how much you predict it's below the current best one, but it also has to do with your uncertainty. It's a synthesis of mean and uncertainty. People talk about exploration and exploitation. It's balancing those two things. Okay, I'll show you an example, and actually I cribbed this example from Matthias Schoenlau's paper with Will Welch. So I just fit some simple data. I've got 5 XY pairs at the top. I did a basic Gaussian process fit. And then I developed a function that I called EI that takes the predictive equations and does this combination with mean and standard deviation. So here's a view of that. The predictive surface is on the left, and the expected improvement, which is this lens through which you look at the predictive surface for the purposes of optimization, is on the right. Most people would maximize that expected improvement surface. So the next acquisition would be at like 2.5 or something like that. You would choose that as your next run, and then when you do that, you squash down the potential for further improvement at that location, and now you've got another place to try, for example, around 8. And you can kind of see if you look at the predictive surface on the left here, right? Although my mean is high, near 8, I've got a lot of uncertainty, and some of that distribution is below the current best location. So it makes sense to explore there. There's potential for improvement. Okay, so that's the tutorial part of my talk. Now I want to survey some things that are on the frontier, and I'm going to go faster because I really want to make sure I have time at the end to talk about deep Gaussian processes. Probably the biggest boogeyman for Gaussian processes is working with an n by n covariance matrix, a dense covariance matrix of inverse distances. You need to invert that matrix. You need its determinant. So you need a decomposition of that matrix, and that's cubic in n if that matrix is dense. There are a lot of good ideas for making the matrix sparse or low rank so that you can do that decomposition faster. And I've got a bunch of papers. There are 5 or 6 there, but actually there are 500 or 600 probably. Okay, I'm going to tell you about 2 ideas very quickly. One of them I think is the simplest, and it's one that I've worked on. Another one I think is the best, and I'm going to do those 2 in turn. So the simplest you could think of as a local divide and conquer. If you want to make a prediction at a particular testing location X, maybe you don't need all of your training data. If you have 1 million training data runs, maybe you don't need all of them, because this distance-based idea is decaying very quickly as you get away from that testing location. If instead you took a nearest neighbor kind of approach and took just nearby training data and did the calculations with that subset, it'll be a lot quicker. And you can determine that subset either by distance purely, so that's a nearest neighbor idea, or what I'm showing you on the right here is through a design principle. These red locations are the locations that you've estimated to reduce your predictive uncertainty the most, given the constraint that you only take, say, 50 of them instead of all of them. And you can solve for that pretty quickly and get accurate results. And then you can scale that up if you want to make predictions over a whole grid. So I took a training data set that had about 40,000 training points. You cannot on a laptop decompose a 40,000 by 40,000 matrix. You don't have enough memory for one thing unless you've got a really big RAM, and RAM is expensive these days, but it also takes a lot of time. But if you want to predict at a dense grid in this two-dimensional input space, you can divide and conquer. You can make a bunch of independent local neighborhood calculations and use all 32 cores of your big workstation, or even laptops these days have a lot of cores, and you can do it pretty quickly. Here I've predicted at 10,000 locations in under a minute and made this surface. The second idea, which I think is a better idea, but more complicated to explain, is called the Vecchia approximation. So if what I just showed you is a divide and conquer, it's kind of implicitly making the covariance matrix sparse away from where you're trying to predict. The Vecchia approximation is making the inverse of the covariance matrix sparse. And the idea behind it goes like this. Any joint distribution, here I've just got 3 random variables, but any joint distribution can be factorized as a product, or I call a cascade of conditionals. And you can do that in any order that you want. And then you can make an approximation by dropping some of the conditioning elements. And when you do that, you are making the inverse of that covariance matrix sparse. You can do this in any learning setup. The likelihood is one of these joint distributions, and you can write the likelihood as a product of conditionals or a cascade of nested conditionals. And then you can drop some of the conditioning terms. When you do that with a Gaussian distribution, with a multivariate normal, you get what's called a sparse inverse Cholesky factor. In other words, you can do the Cholesky decomposition of that matrix with relatively standard algorithms, also in parallel, and it's very fast. So like I said, this is a little more complicated conceptually, but this is actually a better idea. It's a better idea from a technical perspective. It's more satisfying than the nearest neighbor approach. It also is faster and more accurate, which I'm trying to show you, but it's not worth dwelling over the details. Another thing I want to tell you about is variance. I said I would. If you have a simulation or a data collection mechanism where not only is the mean changing nonlinearly as a function of the inputs, but so is the variance, so is the amplitude of the noise, you can do that no problem. Just put a Gaussian process prior on the variances. These are latent variables, but you can do that and you can do the learning. You get a kind of complex looking log likelihood that involves order n latent variance variables, one for each training data pair. But this is the likelihood. If you can take derivatives, and you can, then you can maximize it, or you can integrate it out under with elliptical slice sampling or something like that. It's a wonderfully numerically efficient scheme. I'm going to show you one package just as a kind of demonstration that fits the so-called motorcycle accident data. So this is just a 1D data set. In 1D, I can make nice pictures, right? And you can see that I'm fitting the nonlinear mean, and I've got error bars that are changing in magnitude as I go from left to right. And my estimate of the predictive variance is this weird nonlinear function. And I learned all that directly from the data with 2 Gaussian process priors. One of them is for the mean, like I talked to you about at the very beginning of the presentation, and the other one is for the variance. where I'm dialing in a nonlinear variance function along with the mean. All right. I also wanted to talk about calibration, but Rob, how much time do I have left? I really don't want to go into your coffee break. This is a faux pas. How many? 20. Oh, great. I'm still going to skip this, though. Calibration is wonderful. This is where you have two data sources, like a physical experiment and a computer experiment, and you want to use those two together. Or maybe you have multiple resolutions for your computer experiment. You can do that. All you got to do is stack multivariate normal distributions. It's pretty straightforward. But I'm going to skip it. This is the last thing I want to talk to you about. I want to talk to you about regime-changing behavior, and I don't mean Iran regime-changing. It's not about that. So here's a test function that I'm going to plot for you in a moment. And you can see in the comment here, this function is part wiggly and part straight. And Gaussian processes really struggle because they're based on distance, and distance is measured the same everywhere. So it's a stationary modeling enterprise, at least when you use inverse distance solely. And that means when you have some function that's got two different regimes, where it's a little bit wiggly here and more straight here, it doesn't work so well. So here's the visual of this function. So the inputs x are equally spaced, but you can see the outputs are not equally spaced on the left and on the right. I've got a much wigglier function on the left, and I've got a straight function on the right. But since the same dynamics are involved everywhere in the input space, because it's just inverse distance, it's just that relative information, not the absolute position itself, that matters, I'm getting, at least in my opinion, I guess it's hard for me to convince you if you haven't seen a lot of these, but I think I have too much uncertainty here and not enough. I'm overconfident over here. I should have more uncertainty in the left and less on the right, because my response surface exhibits non-stationary dynamics. But I'm fitting it with a stationary Gaussian process model that only cares about distance and not about position. Here are, I don't know, 5 or 6 papers where people have tackled this problem. And again, there are probably 500 or 600 papers. But I'll tell you about a new exciting one that's called deep Gaussian processes. This is largely the work of a PhD student of mine, Annie Booth. But we didn't invent deep Gaussian processes. However, we have a new kind of way of looking at them that I think is computationally tractable and powerful. What is a deep Gaussian process? It's making an analogy, hopefully, to you with deep neural networks, right? But it's not neural networks, it's Gaussian processes. What are deep neural networks? They are chains or compositions of neural networks. And that's what a deep Gaussian process is by analogy. It's a chain or composition of Gaussian processes. And I really like this diagram because I think it gets to the heart of it. The first half, or 2/3 of the talk, I told you about a typical Gaussian process, an ordinary one. That's the first panel here. I've got x's, and I can generate y's. I'm calling them y1 because I want to talk about y2 and y3, but it's just x's generating y's. Now, if you take those y's and you put them in as inputs to another Gaussian process, so the outputs y1 are becoming the inputs of a second Gaussian process and generating some y2s. So that's the way in which it's a composition or a chain of Gaussian processes. And you can keep doing that if you want to have very deep or multi-layered Gaussian processes. But it's surprising what you can do with just 2 of them, with just one latent Gaussian process, if you will. On the x-axis here, we've got this rug, right? The rug is kind of uniform here, but then the rug gets stretched out in the middle and compressed at the edges. So this is me showing you that because this function is stretched out in the middle and compressed at the edges, what it's effectively doing is warping the original inputs. If you think about that function of y2 given the original x, it's as if the original x's were spread out in the middle and compressed at the edges. So it's in this way that through the composition, I'm going to take position information into account when I use otherwise stationary distance-based covariances. So Gaussian process 1 is using a distance-based covariance. Gaussian process 2 is using a distance-based covariance. But in between, there's some position that's moving around through the latent Gaussian process, giving me a non-stationary capability, giving me the ability to take position information into account. Now, learning isn't easy. I've created a latent variable y1 when modeling y2, for example, and I've got to learn what the data tell me that that latent variable is. Now, here I've changed my notation a little bit. I'm going to focus on a 2-layer deep Gaussian process, and I'm not going to use y1 and y2. My outputs are just going to be y and my inputs x like before, but my latent variable is called w, because I really like to think about it as warping the original inputs. I'm going from x to w. I'm learning some new features, w, by warping the original x's, and I use those to model the y. Many techniques work for learning this warping. You can do variational inference. You can maximize the likelihood. You can use inducing points and so on. What I really like is elliptical slice sampling because it's fully Bayesian. It's easy to code up, and I can look at all of the warpings that explain my data. I'm not going to go into elliptical slice sampling. Fantastic method. Whenever you have a Gaussian prior or multivariate normal prior, which is what a Gaussian process is, elliptical slice sampling is a wonderful tool. Okay, here is what you get when you fit this simple example. You get much tighter uncertainty in the easy region and much wider uncertainty in the hard region. And how you get that is through this warping. You find a high slope warping on the left and a flat warping on the right. So you stretch out the distances in the left half of the space and you compress the distances in the right half of the space. And that gives you differential ability in different parts of the input space. We've got lots more examples that I don't want to spend a lot of time on. Here's a 2-dimensional example where the warping is a 2-to-2 warping. We did a bake-off in 4D with this function and found that deep Gaussian processes, or 2-layer deep Gaussian processes, were much more accurate than ordinary ones. And we used the Vecchia approximation that I explained to you to make this computationally tractable for moderately large training data. I wanted to get back to this motivating application. So this is where I want to wrap up. Rob, am I doing good still? Oh, we're going to be great. I got 5 minutes left, and then 5 for questions, and then we can all get coffee. All right, so we have an existing data set in this 7-dimensional space. So a space-filling design of those 7 coordinates. 500 runs were planned, and then we have a holdout 4,500 testing set, and we did a little bake-off between deep Gaussian processes and ordinary Gaussian processes, and a competitor deep Gaussian process way that used variational inference instead of elliptical slice sampling. And what we found is using deep Gaussian processes on this data is important to get the most accurate prediction, and doing it with elliptical slice sampling is way better than doing it with variational inference. That's the summary of this slide here. Why does that happen? That happens a lot in aeronautics or in fluid dynamics because there's very different dynamics involved in, I'm not an expert in this, by the way, I'm just telling you what my collaborators tell me. For example, near the sound barrier, right? The physical dynamics or the fluid dynamics are way different below Mach 1 than above Mach 1. It's fundamentally different. And so if you take the same modeling apparatus in both of those two regimes, you don't do as well as if you can learn how the dynamics evolve as a function of speed, for example. And speed is one of the inputs. Okay, we were really interested in a reliability problem with these data. We didn't want to just build a model for prediction. We wanted to know where the safe and unsafe operating regimes are for this aircraft. And we defined pass and fail. Oh, good. We're both on the right, same slide now. Good. We defined this failure. Oops, I didn't mean to go to the next slide. Don't go to the next slide. We defined this threshold here that separates passes from failures. And then we measured our sensitivity and specificity to that classification problem. So it's a regression, but it's inducing a classification into success or failure. And our methods still are the best for this goal, but the question is, this was just a space-filling design. Could I have done better with less training data that focused on the level set that separates passes from failures? So I'm not trying to optimize the function. I'm trying to find a contour in a 7-dimensional space that separates these two classifications from one another. And you can do that. There are, again, many acquisition criteria that target this. The very simplest ones are based on entropy. You've got a classification. You've got probabilities that come from Gaussian cumulative distribution functions that define those probabilities through the Gaussian process. And you can calculate the entropy of that probability distribution, the classification between pass and no pass. So this is just a slide that says that. It's a little bit overkill. Here's a simple example in 2 dimensions. So I have a simple function that's, it's steep. Oops, I did it again and hit the wrong button. I want to go back. It's steep here, and I'm trying to learn about this contour. It's the 0 level set. Here's my predictive mean is on this. This is not the actual data, it's my prediction. This is my uncertainty, and this is the entropy. It's the lens through which I'm going to look at the predictive distribution. Expected improvement was the lens when I wanted to optimize. Now entropy is the lens when I want to find this level set. Now I've got to find the part of this that maximizes, right? The maximum is near here, but that's actually kind of hard to do, even in this 2-dimensional problem, but especially in 7 dimensions, because a lot of the input space has numerically 0 entropy, making it very difficult to find a gradient that's numerically stable in order to find where this surface is maximized. So we put a bit of effort into a strategy for doing that, but it's not super interesting, and so I'm going to skip it in the interest of time and just show you that using this entropy active learning is really efficient for finding this contour. I can get sensitivities and specificities that are both high, that are both good, with many fewer training data runs of this. And we made some comparisons to other methods, and we also made some comparisons. So these are the other methods. This is average case behavior, and this is under Monte Carlo repetition. But we were almost always the very best with a finite budget of runs. This was on a toy problem. Back in the airfoil, we weren't able to do as many comparisons because running the computer code was very computationally intensive. But we got the same results. We were able to very efficiently learn this quality problem, this separation of pass and failure. So that's what I wanted to talk to you about today. My last slide is just sort of more info. Annie's PhD dissertation, which is all this deep Gaussian process stuff and active learning and the airfoil problem, is published, and we have code for it in a Git repository. This has always been very important to me. I think you have to not just release your code, but make it consumable by other people, because we live in a time where everything is complicated and you cannot recreate this stuff on your own. But I've worked really hard, and I've encouraged my students to work really hard to make that available. So you can get that. Everything before that in the presentation is basically material that went into my book. And the book is set up very similarly. It's reproducible, it's R, it's in R Markdown. It's free. I'm not trying to sell you anything. You can buy a copy if you want to, but if you go to my webpage, you can get the HTML and PDF versions of the book, and you can cut and paste the code and see how it all works. Thank you again. Thanks, Rob. Thanks, the Statistical Society of Canada. It is a thrill to be here. Thanks for your attention.
Okay, thanks so much, Bobby, for a wonderful talk. Are there any questions for our speaker? Yeah, over there. Do you want to come and use one of the mics so we can hear you?
Great talk. Oh, that's loud. This might be in the book, but my question is about, like, in the layers of the deep Gaussian process, is there any value in, like, having a covariance structure that's different on each layer? Or do you use the same structure on each?
That's a great question. By the way, the deep stuff is not in the book because it's kind of newer. Wonderful question. We do use the same covariance structure in all the layers, but we use a simpler covariance structure than you would ordinarily use if you were just doing an ordinary Gaussian process. This warping, this latent variable that you learn is highly flexible, and it benefits to regularize your Gaussian processes at each layer a little bit. So the answer was no, but also kind of yes.
Cool, thank you.
Alex?
Bob, thank you. Great talk. For your variational inference, which variational family are you using?
Let me clarify that our competitors used variational inference, and we just used their code. I don't remember. We do not use variational inference. We use elliptical slice sampling, which is full, there's no approximation. It's full posterior inference by Markup chain Monte Carlo.
And for the, because I'm curious about the alternative algorithms, it's for my own interest. For the maximum likelihood estimates that you get, we know that the variance and the range parameters, they tend to be highly correlated. And the posterior tendency of the likelihood tends to be multimodal. Did you experience any sensitivity? Values or something like this?
Alex, you're absolutely right. I only used a maximum likelihood for this presentation and also in the book for expedience. It's really simple to explain. People understand it. But for the reasons that you just said, in Gaussian processes, as in almost any learning enterprise, there's a tension between signal and noise. What you're talking about, length scale and nugget, those are the signal and noise parameters. And it can be sometimes very difficult to decide between a low signal, high noise, sort of flat surface, or a very wiggly, high signal, low noise. And the only way to do that effectively, I think, is through Bayesian posterior sampling and a really good Monte Carlo method that allows you to explore that whole posterior.
This is what I wanted to hear. Thank you.
Okay, I don't see any more hands. I guess this means everybody does want to stick to time and make the coffee break. This is slightly embarrassing. At this point, I was going to give you a little gift that we purchased. I've left it in my hotel room. So I will get you the gift maybe later today. But thanks for a brilliant talk, Bobby.